Hello and welcome to another video. In this tutorial I'm going to continue with some examples on how we can use particle swarm optimization to minimize or maximize a function and do some visualization to understand how the optimization algorithm is actually working. Now for visualization purpose, I'm just going to use a 1D function. And the first example is a sine of x. And we can choose a different number of particles. Here I'm going to choose 20 particles. Typically 10 particles are enough for a 1D function, but here I'm going to choose 20 particles. Okay, so 20 is the number of particles. And if for the sine of x, we know that it has a minimum and a maximum, exactly a maximum and a minimum in the 0 to 2 pi interval. So I'm going to choose 0 to 2 pi. And the first objective is to maximize, and then the second objective is to minimize, right? So we can either maximize and minimize, and if you recall, we just implemented a flag in the PSO that determines whether we want to maximize or minimize. So by default, the PSO that we implemented in Java was trying to minimize the function. All right. Now here I have two cases, and this is my function. I have already plotted this. The title of the plot tells us which iteration step we are looking at, and it starts from iteration 0. And I'm going to do 10 iterations. All right? So 20 particles, 10 iterations. Maybe let's just, okay. Sine of x, and let's see how the maximization works. So at iteration 0, this is the blue curve is the actual plot, and the red curve, each red dot or red marker represents a particle that we have chosen, right? We have created a particle. Now we have 20 particles here, and at iteration 0, these are the original particles that have been randomly selected in this 0 to 2 pi interval. If you recall, we said that when we create a particle, we set its position randomly in the dimension of the variables, which is just one dimensional here. Okay, so we have 20 particles almost uniformly, randomly and we select them with a uniform distribution. Okay, and then I have just calculated the value of the fitness function for each particle. All right, so if we go to the next iteration 1, you see that after one iteration the particles are starting to move towards the peak, which is the swarm's objective, the optimization goal. In the next iteration 2, you see most of the particles are reaching to the peak very quickly. In the iteration 3, almost there. We still have a few particles around the peak, not quite there yet. In the iteration 4, we're pretty much all the particles converge to the max. Basically, this means that the swarm is actually moving towards its objective. And remember, the objective is predefined. We set where the swarm should go. All right, so iteration 2, iteration 3, iteration 4, iteration 5, pretty much there. So with 5 iterations, the swarm has already reached the peak. Iteration 6, still a little bit more convergence. Iteration 7, we are practically there. So we see that with 7 iterations, the PSO, the particle swarm optimization that we implemented, basically converges to the peak. And with the next iteration steps, nothing actually happens. The swarm is already there. There is no update. And actually, this is a movie, so if I just play it, you see that step by step how it happens. All right. Now for the minimization, we set the PSO minimization flag to true. So this, if you recall, the then the swarm's objective is to go to the minimum of the function. And again, frame by frame, if we look at this movie, at the iteration 0, we have subparticles randomly selected, and it's supposed to be a uniform distribution in the beginning. In iteration 1, you see the particles are moving towards the minimum point. In iteration 2, most of the particles are pretty much there. Iteration 3, almost there, still a few particles not having enough momentum to reach. Iteration 4, we are almost there. Iteration 5 pretty much reaches the minimum, the swarm is all there. Iteration 6, the convergence is fixed. And iteration 7, we have full convergence. And after iteration 7, nothing happens. You see, all the particles are here. And let's play the movie. Okay, and I can also go full screen to show you to play the movie. So let's play this one, iteration step by step, 7 iteration, 9, 10, and this one 6, 7 iterations. And as you can see, we can see a step by step what happens in the iteration. Okay, and so the next example is again a 1D function, one-dimensional function, but it's a little bit more complicated. It's a sine of x squared, and I again have 220 particles, and I'm looking at the 0 to 2 pi, 0 to pi actually, 0 to 3.14. okay. Now in this region, the function has 2 maxima and 1 minimum. So let's see what happens if we try to maximize the function sine of x squared. So frame by frame. So at iteration 0, we have some particles completely randomly distributed over this particle, over this interval. Iteration 1, they try to start, or the particles try to converge to a peak, to a maximum. Iteration 2, pretty much there. You see how fast it is, and as you can see, there is one particle that is trapped at this minimum. That's also very interesting. So at iteration 3, that particle that was trapped actually can get up and join the swarm again, so it's not left behind anymore, and most of the swarm is already there. At iteration 4, almost there, very good convergence. At iteration 5, 2 of the particles try to lose their ways and come out, but I guess at the next iteration they go back. Yes, they go back at iteration 6. Iteration 7, the convergence is complete, all of the particles there at the peak, and after iteration 7 nothing actually changes, so the particles don't move anymore. Iteration 8, iteration 9, iteration. Okay, so let's play the movie one more time. Okay, so one thing that you need to understand is that the PSO doesn't guarantee any optimal solution. It might very well fail, okay? But in these simple cases, for example, sine of x squared or whatever, these simple functions, we know that we have a maximum or minimum. That's one thing. The other thing is that I know that in the interval of 0 to pi, I have 2 maxima for my function. The question is, if I distribute the particles randomly, which of these maxima the PSO actually converges to? And the answer is, it's completely random. We cannot tell. We cannot really tell. So, and the question is, do we care about which? If we just want to maximize this function, we don't really care that much about which of these maxima we actually hit. And note that both of these maxima here are global maxima, not local, right? And we talked about one of the coefficients in the equation for the velocity, which was the inertia weight, and that determined whether or not the goal is to reach a local maximum or a global maximum. Similarly for local minimum or global minimum. And I mentioned that you can read the literature about how to vary these parameters to set the PSO to a global optimization or local optimization. Okay, But here we're just looking for global optimization, global max, and it converges here. Maybe if we run it another time, the swarm might converge to here. Okay. Now for minimization, we only have one global minimum here, so the swarm should definitely converge to this point. And another thing, when you compare these two side by side, you see that the particles are at different locations, because each time you create particles, it creates a different random distribution, right? So at iteration 0, we have these 20 particles. Iteration 1, they pretty much try to converge to the minimum. Iteration 2, the swarm, some of these particles actually lose their way. So if you recall, most of the particles, most of these are trying to get here, but then at some point some of them get away from the swarm. But I assume that they're going to come back. So let's see. Yes. So in iteration 3, at least 19 particles have pretty much reached the optimal point. There is one particle still left here, and then in the next iteration, almost there is one particle close, and at iteration 5, pretty much all the swarm is there at the minimum, at the optimal point. Iteration 6, the convergence is complete. All of the particles is at one location, and no change will happen after iteration 6. Okay, so let's play the movie. Let's go again, and I'm going to also go full screen to play the movie. And you can clearly understand how this particle swarm optimization is working. It's very interesting how it pushes the swarm, all the particles, to the global maxima or minima. So this one is for minimizing the function, and as you can see, all the particles reach the exact same location, which means a full convergence. Now the question is, how many, if we are given a function, how do we know how many iteration steps we should take? And the answer is that we can implement some if statements or convergence tests in the PSO algorithm in the Java code, which I didn't do because typically, at least for 1D functions, the convergence is pretty fast. So 10-20 iterations should get you to the optimal point. As we can see here, with just about 6-7 iterations, we are almost there. And the beauty here is that this function we don't have any requirements on this function. So the function could be discontinuous, could be very badly behaved. It couldn't. If the function is not smooth, we don't care. We're not calculating the derivatives, so we don't care really about the behavior of the function. Any discontinuity or anything is fine. Alright, so the question is, you're probably wondering how I created these animations, okay? And in order to create the animations, I'm using a ImageJ library in Java, and it also is available as a standalone software for Mac, Windows. It's an open source Java library. You can just search ImageJ on Google and you can find the library. It has good capabilities for image processing. So if you're doing image processing in Java, this is definitely the library to go with. So for creating these animations, I'm just using the standalone application, ImageJ on Mac, and what I'm going to do, basically, I plot the function, and at each step of the iteration for the PSO, I'm getting all the particles, all the positions of the particles, and evaluate the fitness function at that positions and just plot them as another function, okay? And then at each iteration step, I'm saving the figure, the plot, as a PNG image, and I include the iteration step in the name. And then if you put all of the images in a folder, you can import them as an as an image sequence, or a sequence of images in image.j application. And then from that you can export the sequence of images as a GIF or movie, AVI movie. Export as AVI movie. So these ones here are AVI movies that I have exported them. Okay, so let's go to Eclipse and see how the code looks like for generating these movies. So in the demo PSO project, I have created a test package, test PSO, and here's the test PSO. Okay, so I have put two tests here, test 1 and test 2, and first I'm going to run test 1. In test 1, first of all, I create my fitness function using a lambda expression. So I have the lambda expression here, and again, this fitness function takes an array of variables. So the input is an array. So if I have t as my array and I have only 1D, I have to use t index 0 to show that it's a 1D function, 1D array of parameters, right? So I cannot, if I just use a sine of t, this returns an error. So I have, because t here is assumed to be an array, so I have to use t0, which automatically says that, okay, the implication here is that this function is one-dimensional. And then I create my PSO object, 20 particles. The first argument is number of particles, the second is the fitness function, and the third is the intervals. Okay, and I'm going to search for the optimization in the 0 to 2 pi interval. And if you recall, this interval function or method is a static member of the PSO class. So I have already imported from the PSO class all the static members. That's one thing. The other thing is that if you recall, I mentioned that I prefer to have this interval as a class level access, so the user doesn't need to use this. But the problem is that if you make it a default access, just visible to the package, then you cannot use this static method, because the compiler says that, okay, this method returns an interval object, but it's not supposed to be accessible outside this package. That's why the compiler is complaining. So we have to change the access level of the interval to the public. Similarly, for the particle, I change it to the public modifier, and then for vector nd, because the vector nd keeps track of the values for the positions of the particles, it's also public. All right, because we need to access them here. So what I'm going to do, I'm going to set the minimization goal to true. So we are actually, our objective is to minimize. If we set it to false, the objective is then to maximize. All right, and I'm going to have 10 iteration steps. So here, doing iterations, 10 iteration steps. And the reason that I'm putting this in a for loop, because I want to solve the PSO for this given number of iterations I, which goes from 0 to 10. So I want to solve first for the 0 iteration, and then plot it, and then save it, and then I want to solve the PSO for actually basically 2 or 3 or 5 number of iterations. Okay, and then basically what we can do also, we can also put this one inside. So we create the PSO, inside the for loop. So, and then we set the minimize to true. We solve it for I times of iteration. I'm also putting the printing the best value of the swarm and the best position of the swarm, and then I get the number of particles. I created this method, get number of particles, in the PSO, which just returns the number of particles. And then I create an array called particles position. Remember, each particle is one dimensional, so this array takes all the positions of all the particles, and then I do a for loop to get the position of each particle. So from PSO I get the particles, which just returns a list of particles, and I get the kth particle. This is just inside the list API. So this returns a particle, this get particles returns a list of particles, get returns a particular particle in that list, and then get position returns a vector nd, and this vector nd is one dimensional. So if you recall, we defined this method at index I, which returns the ith element in the vector nd. And because we know that these are one dimensional vectors, we just get the index 0. And this is basically the position of the particle kth particle in the 0 to 2 pi interval. And then I calculate the values of the fitness function using the array func in the mathlib project. If you go to mathlib, from the util, from the func, there is a array func, and it has an interface for passing in a one-dimensional real function, and it just iterates over the array and returns the basically a for loop that evaluates this one-dimensional real function at each element of the array. Okay, so I define a lambda expression for the function interface, which is func.value a. Note that this here a is not a vector like here, right? A is a real number. And then I calculate this value of the function at all the positions of all the particles. All right, and then what I'm going to do here, I'm going to basically I'm going to create a MATLAB chart, a figure, and again the MATLAB chart class is a wrapper that I wrote for JFree chart. If you are not familiar with the JFree chart, we will have tutorials on JFree chart in the future, so you can watch them. So the MATLAB chart is in the plot package in the mathlib library, and it has very convenient methods for using the JFree chart. So I create a MATLAB chart, I call it fig, and then first I plot the function in the over the 0 to 2 pi interval. So double x, I'm using the linear space function method, the linear space method in the mathutils class that I wrote. It's in the mathlib.util package. So 1000 points in the 0 to 2 pi interval, and then I evaluate the function at these points and then plot them. This is figure 0, and then I plot another function which is the particles position and particles fitness values. I plot them with the color red, so the default color is blue, and then I render the plot to create the JFree chart. Set the title to iteration I, set the x limit to 0 to 2 pi, set the y limit to minus 1.1 and 1.1, set the x label to x values, set the y label to fitness function, and the default font, I believe it's 9, the size of the default font. So if you call the font and pass in an integer, it assumes it's the font size. So I'm passing it 13, increasing the font, increasing the font size, and then I'm going to so by default markers are off, so I'm going to add markers to fig number 1. So if you call the marker on with passing an integer, which is the figure number, so I'm turning the markers on for the particles, and then I'm going to set the line width to 0. So I don't want to have any line width for the the second plot. I just want to have markers, and each marker represents a particle. Then it is easier to see how the particles are moving on this function, right? So each marker represents a particle. And after that, I call the save as PNG method, and the save as PNG method just calls the chart utilities class in the JFree chart, and then calls the save chart as PNG. Okay, and it takes care of creating a file and passing it a file name. Okay, so save as PNG, and I have in the project, let me refresh this, I've already created a folder example, so I'm putting in the example folder, I'm saving the plot as a PNG. The name of the figure is iteration underscore I, and I is basically the iteration step, and the width is 500 pixels and the height is also 500 pixels. So something like this, you can create a figure and save it at each iteration steps. And the way we're doing it, we're solving the PSO for that particular number of iteration each time in each step of the for loop. So if I run this, let's save this. Now this also shows that basically the value of the best value of the swarm, the best position and value, and we see that eventually it reaches -1, and then all the figures are here. So let me just close them and open them one by one. So this is iteration 0, we have some particles randomly around, iteration 1, iteration 2, iteration 3, iteration 4, iteration 5, iteration 6, iteration 7, iteration 8, iteration 9. Okay, and you see that they are reaching the minimum. So if I go here, let's run it for 20 steps. I'm going to delete these. And it's going to run. Eventually it has a very good convergence, and we have about 20 figures here. Okay, and now what I'm going to do, I'm going to call image J application, and in the file menu I have an import option here, and I'm going to import all these PNG figures as image sequence. In the example folder, you just select it, it automatically recognizes that we have 20 photos, pictures, starting image 1, increment 1. It already recognizes the numbering here, figure name contains, doesn't matter, and okay. So it has already imported 20 figures starting from iteration 0, and we can run it as a movie. As you can see, the swarm is converging. Okay, so that's how it creates a movie of all these frames. And then if I want to export it, I can go to File, Save As, and Export as AVI movie. And I don't want to have any compression to reduce the quality, and you can set the speed or the frame per second FPS. I'm going to set it to 3, and then you can save it wherever you want. I'm going to save it in the examples folder, and then you can play it with any video player. Okay, so that's test 1. Test 2, if you recall, was sine of x squared. So again, when we define the fitness function, we have the input. If we're doing lambda expression, we have to be careful because t here is a vector or an array. So if our function is one-dimensional, we can have we should use t index 0, t0 times t0, because t is an array. Unlike here, when I use the apply, which here basically this interface, this lambda expression represents an interface that takes a real value, a one-dimensional function, so takes a real number and maps it to a real value. That's why here I'm not using a index 0, because this interface is different from this interface. But that's the convenience of using lambda expressions, right? The same things, basically I am going to put the PSO and its flag inside the for loop, and we can run this and we get the same result. Okay, now instead of saving it, I can just show it on the screen. So fig.show with a true flag for exiting the JVM or terminating the program after execution. So it's going to create let me see. Let's see, fig.run. Okay, that's because all right, that's because I'm running test 1. Let's run test 2, and then we can use the run or show method for showing the figures on the screen. So after 9 iterations, you see what happens. Iteration 2, iteration 1, iteration 0, and we can close all of them by pressing on the stop. So that's how you can create a sequence of frames of your optimization process and then turn them into a movie using image J library. I hope this was useful. Thank you for watching, and I'll see you in the next video.